Testing, and the topic in demand today, cybersecurity and resiliency. So over to you, sir. You can start. Thank you.
Very good evening to all of you. Welcome you all to this mighty course on fundamentals of smart grid. And today's topic will be cyber security and resiliency. Before we move forward, let us understand what is cyber physical system, that is known as CPS. So first of all, we'll try to understand what is cyber physical system, and then we'll try to understand how cyber physical system and resiliency are strongly interconnected, and then we'll move to our next levels. Now, a physical system is nothing but a hybrid AC-DC microgrid. Assuming, okay, so we learned a DC microgrid, we learned a AC microgrid, we learned a hybrid AC-DC microgrid, and that is known as my physical system. Now, this physical system do have actually a bit of communication component, okay? And communication component means like the controller, the devices, they communicate with other devices within the same system to carry out energy balance, control mechanism, day-to-day operation, okay? Islanding operation, grid, coming back to grid mechanism. So all these operations happens through a reasonable communication in phase, because we are not doing anything manually. They all talk to each other. And when they talk to each other with a kind of a communication layer, so the physical layer and that communication layer, which is a form of actually a cyber, So cyber means which is prone to breaking strategies, prone to prone to communication failure, and prone to system jeopardize. Okay, so that layer, which is a communication layer above a physical system, popularly known as cyber layer. So we have a physical layer, we have a cyber layer, and both together known as cyber physical system. Is it okay? And so what does it mean? A cyber physical system is more advanced technology, and where actually each and every component can communicate to each other, but the limitation is failure to which will lead to catastrophic challenges, or I can say jeopardize of the system may happen due to failure of the communication links. Okay. Then we talk about resiliency. What is resiliency? Resiliency means a system which can come back to its normalcy after a failure or a problem. So only when you have a system, a physical system which has been linked to a cyber layer, they only can come back to normalcy quickly, because there is a strong communication happening. Am I right? So any failure, any challenges, you have a system, a small portion is actually islanded due to a challenge, okay? Once the system is normal, then this must again come back to the normalcy, okay? It means come back to the system. So coming back to the system means that is a normal operation as it was in the earlier days. And the capability of the system coming back to normalcy is known as the measure of resiliency, okay? So how Manmohan, how resilient he is under stress. Okay? It's a measurement, okay? Sometimes you are not able to come back to normal. Stress rehta hai pura, And sometimes it takes one day. And sometimes you quickly come back. So you face stress class, somebody disturbed you when you are teaching, but you are not getting irritated and coming back to normal, though you got irritated. And that is known as, he's a resilient professor who doesn't get affected with the disturbance of the students.
Robust and resilience.
Hanji?
Robust and resilience kind of.
Robust is different. Resiliency, robust is different. Robust means Robust means actually, no, it will have the resistance up to that an extent, it will not be affected also. And then it will fail. Robust, and then finally it will fail. But resilience is not the resilience is welcome failures, but it has this inherent capacity to come back to its normal operation after some time. So that is resiliency. So cyber security and resiliency both are very, very important concept in the modern distribution system. And let us see how we'll be able to touch upon those theories. Hope you have understood the concept slightly. What is cyber physical layer? What is cyber security? What is cyber security then? We talked about cyber physical layer. What is cyber security? Cyber security means a security level being embedded in the cyber physical system, okay, which does not allow a malware to affect your system. That is my cyber security system. Okay, very good. We'll talk those fundamental uh, cyber physical system background. We'll then talk about cyber physical system components, pros and cons of cyber physical system, cyber adversaries classifications, cyber security, cyber resilience, cyber anomaly detection methods, centralized and distributed techniques, potential research scope. Huh? So today we'll also see one more PhD topic during end of the class. Okay, good. And this is how actually a system look like. Okay, so what is a cyber physical system? The integration of physical and cyber system evolves into a new digital technology called cyber physical system. So as you could see from the right hand side bottom, we have a complete physical layer, that is your AC/DC microgrid, or could be a distribution system, could be any system. And then you have a communication layer at the top, which is popularly known as the cyber layer. So this whole become a single cyber physical layer. Now, how we interact with the physical power system would around us? What is the role of CPS in our conventional electric power grid or microgrid structure? So there is a question people may ask actually, why do we talk about cyber physical layer? Anyway, I see my bulbs, I see my supply, I see my substation, everything is in place working so nicely. Distribution system and isolated microgrid structures are evolving with massive and unprecedented deployment of smart grid technology. Okay. So in the past, actually, we had a very conventional system. There is a substation, switch it on, people will get power, there is a cable, everything is okay. Now you integrated PV into that, you have integrated wind power into that, you have integrated storage into that, and then you started optimizing storage, when to charge, when to discharge. How can I have one cycle of charging, discharging every day? Then you say extract maximum power from the PV, extract maximum power from the wind. Then you say, oh, during transient have some supercapacitor also. What is this, Baba? We made the system too complicated in the process, and hence new business model and the addition of new stakeholders in the process of adding many devices. Okay, and then we say all the inverters start talking to each other. We have a derated mechanism of energy, a multi-microgrid concept, different control architectures. Am I right? So it's too complicated now. Okay. So because of which the cyber physical system become important. So what are the physical components we see in the power system? Plants, sensors, actuators, and whereas in cyber we do have communication networks, protocols, intelligent electronic devices, Internet of Things, and so on and so forth. I will tell you one example. Even the replacement of conventional electric meters by a smart meter, okay, and then getting those datas and processing how much energy to be made available to customer during upcoming Diwali become a case study, okay, and that is where your devices actually play an important role. Now you see those smart meters, they communicate to a control center and send their data minute wise, second wise, hour wise, 15 minutes wise, whatever you want. So that means that is where the communication, cyber physical layer comes to action again. So what are the benefits? So first of all, two-way flow of information and electricity. Okay, I can talk to my smart meter can talk to me. I can talk to my inverter, the inverter can talk to me. I can talk to my BMS of the battery, the BMS can talk to me, and so on. So efficient, safe, and secure operation of the power grid. So they are mainly made for the more secure operation of power systems. Flexible coordinated operation based on global system variables. Now, what is happening? You have a distribution system, and now you are talking to the transmission system operator. So, transmission operator says, "Give me some ancillary services from the distribution system." You instruct your devices to see to that maximum, ancillary support being given to the transmission system. So this is happening through communication only. Am I right? We are not doing anything physical. So you are not simply a smart grid. You are not only a microgrid, but you are also contributing to the transmission at large in an indirect way. That is what the future is all about. Automation and smart feature of the power grid. You have a SCADA system now. Let's say. So SCADA system, you see everything. There is a command, and your battery is getting a signal from the SCADA system actually what to do, what not to do at a given point of time. But what are the limitations? It is prone to cyber attacks. So that is this good, but is also equally challenging. Okay, so having a credit card is always a better opportunity, but also there is challenge, risk associated. Am I right? So early days people had only liquid cash, okay, and they spend and they don't spend. That's all. There is no risk, excluding theft part. But nowadays, actually, you use the card, it's a very smart card, but it may have a fraud, financial fraud may happen. Okay, communication latencies is an important issue because you are giving a signal, someone to react, but that gentleman is not able to collaborate with your latency. Okay, so there is a time gap. Actually, that is very important. Then packet dropouts, some loss of data, which is very network jamming. Okay, you are communicating, you say network is busy. That cannot happen in a cyber physical system. All the time it should listen to you. And congestion, network congestion become an issue, and malicious control effects. Okay, so these are the challenges with the limitation and disadvantages. Now, adversaries, examples and classification. Beautiful stories actually we'll talk today. Ukraine, we all learn about Ukraine because of the cyber attack actually. And with the recent war with Russia, we become very, the country is very popular along with for medical education. But with those cyber adversaries as well as the recent war, made Ukraine become more, I will not say popular, but I will say being known to most of the young students and graduates of this country. So power grid of Ukraine was hacked in December 2015. Okay, so this is basically a cyber war for the first time. I don't have time, otherwise I might have told you about the story, what I've read. It's a very interesting story, like how the malware penetrated into a PC and then finally created a blackout. Simple virus. A simple virus can create blackout in the country. That is a severe, very powerful. So power grid of Ukraine was hacked in December 2015, but probably hacked means some of the data, some of the password, someone could enter login password, we casually say no, ABC123 or like this, so that because of that. European network of transmission system operator for electricity hacked in 2020. Another cyber attack. Russian power grid in 2019. People again tried to do it for Russia. In 2019, they suffered. Saudi Aramco petrochemical plant in 2017, very small one. And 10 power estate, Mumbai, Tamil Nadu ports came under Red Echo in 2021. Some of the metro stations, everything got stopped actually. So a lot of things happened. It's basically a cyber attack because nobody knew what has happened, why it stopped. That's the reason. So we'll see a different classification, data manipulation attack, how these attacks happens. One is data manipulation, and then there are two different type of data manipulation. We'll slowly learn what is FDIA and DOS. And then FDIA is basically three types: sensor attack, controllers, and communication link failure. And DOS actually talks about suspend communication, MI, TM, and then again they are classified into unidirectional attack and bidirectional attack. So overall, what we wanted to say, how different cyber attacks have been categorized. Cyber security and resiliency. Okay, that's a very interesting phenomena here. So what is cyber security? We already discussed, but let me repeat it. Cyber security describes a company's ability to protect against and avoid the increasing threat from cyber crime. Very straight example. All devices are running the most up-to-date firmware, well-protected antivirus, firewalls, VPNs, antivirus, malware. Protection is running and up-to-date. All software and tools are fixed with the latest patches. Employees at all levels of the business are educated on the potential threats, actions needed to defend the organization. Now, what is resiliency or cyber resiliency? Cyber resilience refers to a company's ability to mitigate damage, damage to system, processes, and reputation, and carry on once systems or data have been compromised. Means I have a bank. I knew some money being lost through credit card fraud, but still the bank is not stopping. Bank is going on or not? Or they say, no, Manmohan, you lost some money, let us stop the process. Because they know you failed, but doesn't mean that everybody will fail. And that is resiliency. That is resiliency. Okay. So company face some challenges, but still it can continue. Or with the normal system still in operation. Because today, if you see, everyone want to take back the State Bank of India to their home, no? Cyber crimes. वो तो पूरा बैंक को घर लेना चाह रहे हैं एक्चुअली, बट ले पा रहे क्या, नहीं ले पा रहे. दैट इज हाउ यू प्रिपेयर योरसेल्फ. ले भी सकते हैं if they are more intelligent than you. So that is what actually cyber resilience. Cyber resilience covers adversarial threats such as hackers and other malicious actors, as well as non-adversarial threats. For example, simple human error. Okay, that is also possible. Example, developing offline or online emergency processes to keep essential functions such as customer services, quality assurance, finance, and security running as well as possible until the breach can be fixed. Now, how do you detect the anomaly? That is very important. So, why anomaly detection methods are needed? There are some problems, but why it is important? So, detection methods are required for mitigation solutions in order to either continue the normal operation of the system or isolate the compromised part. This provides cyber resilience to the system against attack. So when you realize if someone attack all your thermal power plant, so you realize that one thermal plant actually got affected. So instead of allowing the thermal plant affect to other thermal plants, we can isolate that power plant, let that plant go to hell. The rest of the country must be in operation. So they are being actually leveled, level 1 failure, level 2 failure, level 3 failure, and level 4 failure, okay? So power system protection performance affected. Whenever there is a problem, we say level 1, there is some issue. Frequency imbalance due to drop in power generation. Whenever there is a cyber attack, your frequency will oscillate. That is the first signal. It is something like your blood pressure. When you are not good at health, your BP will shoot. Then you realize something wrong. And then sudden drop of the load actually. Suddenly, if the load is suddenly dropped without any reason, it cannot happen, no. All started coming to road and enjoying, that cannot happen, no. some load will be there. No one is going to movie theater. How it can happen? So I think there is some problem there. So
Drop or increase?
anything, both also suddenly increase without Diwali, that is also a problem. So, they are actually level 2 physical consequences. Okay. Um, then malicious command to exciter and prime movers reference setting through SCADA system means it is not about signals now gone into the system. Okay. So first of all, you are feeling very uneasy. That is level 1. Then you say BP picks it up. Am I right? That is level 2. And then third, you see the other, parts actually started malfunctioning. Then malicious demand side response command. Someone is saying you switch off all your lights, or all the smart meters are instructed to be disconnected. Okay. And then finally, you are actually kind of heart attack, BP, and then you got a heart attack. That is your level 3, and the climax is your level 4. So there's your body system is a power system, and how we can see the level 1 problems, level 2 problems. So level 1 and 2 are considered to be reasonable, but level 3 and 4 are considered to be very, very severe. So there are different methods actually to detect those anomaly. Centralized architecture methods, knowledge-based and data-driven techniques, ML and AI methods, and distributed architecture. So there is one approach which is centralized, and the other approach which is distributed. Okay, methods that are robust not only against disturbances and measurement noises, but also against incomplete measurement. Okay, and that is distributed architecture, which is quite strong method. So you can see both the arrangements, centralized communication architecture, where there is a command which goes to everyone and everyone follow it. Okay. In case of distributed, that everyone has their distribution operations centers, everyone is independent and they act accordingly. Now, when I talk about centralized detection approach, there could be, there's state estimation approach, CHI square method, residual based method, binary hypothesis, model free based ML or stats. Now, in case of distributed, we call it centralized methods after approximation, singular value decomposition method, fault detection and identification, observer based methods. Now, moving to what are the potential, because this is a very vast area, that itself is to me, it's a big PhD problem, not one, but it's many problem actually. But this is quite interesting. You can really, experiment in the laboratory and see what are the challenges happening. Even in the transmission system, we can perhaps actually make a substation non-functional through cyber attacks. Possible. Let's say you see those MCBs, no? So whenever there is a fault, you see MCB trips. Now, can I trip that MCB without having a fault? So there is if you can do that, there are many automated switches now. They can be switched off at a distance. So then what will happen? You will again face a blackout. Are you clear? So cyber security, cyber resilience, cyber physical system application are not limited to distribution system, but it can also be for transmission system. I have learned that even big systems like transmission system are also looking forward to a system which is cyber resilience. Am I right? Because they are also, the substations are become modern and modern. They become, quite advanced and smart today. So those substations are good, but prone to cyber attacks. Can do that. Example, when you talk about PMUs, they are prone to cyber attacks because everything, the data is coming to Earth actually through space. I can create a disturbance and give a wrong data. So what I'm expecting 10 gigawatt, it will tell me 100 gigawatt of the load. So then I'll start my generations and then it will vanish. It will go to the 10 gigawatt load. So what will happen? there is a huge mismatch. I ramped all my generators thinking that there is a load increase happening, which is not true. It's gone. Very exciting. Okay. So I request all of you to visit some of the good power industries, especially POSOCO. And POSOCO is now renamed as, I think, the power grid is different. POSOCO is now renamed to the, I think I request everyone to Grid India, very good, very good. I think now POSOCO has been renamed as Grid India.
Controller of India.
Grid Control of India Limited. So I request all of you to visit Grid Control of India Limited office and see how smartly they have managed. Probably, I think that will give an idea how challenging it will be managing a transmission system as well as a complete power system. So area is actually distributed attack detection would be one of the interesting problems. New techniques for distribution systems. Concurrent attack detection, simultaneous attack on multiple communication links, example, need to be identified. A scalable attack detection, extending the detection algorithm to larger scale systems. And detection of other attacks, one technique could identify different categories of attacks. So this is what actually you are expected to do. Please read a lot of good literatures and try to understand. So in this course, basically, we are not teaching what is cyber physical system, nor the attack detection, but I will certainly give you some of the references. Please read them. We have applied to many AC/DC microgrids. So these are the most of the references. I think the fourth one I will strongly recommend IEEE System Journal, Satabdi Jana with NP Party, Cyber Resilient Cooperative Control for DC Microgrid Clusters. This paper very thoroughly talks about cyber physical challenges. And we'll slowly now move to virtual inertia and ancillary support. So once again, there is an interesting question about actually what is inertia and what is virtual inertia. Now, when we talk about microgrid especially, we are replacing most of the required generation by PV as on today, all right? So wind we do have, but majority is being replaced by PV. So what is happening, because when you replace PV, I could have gone for a hydropower plant or could have gone for a super thermal power plant. Instead of that, actually, I'm going for a PV. Now, PV means there is no rotating mass. Now, let me teach inertia first, and then I'll come back to virtual inertia. So, any one of you should have, let us switch on the speakers. Let's understand how my candidates today understand about inertia. Who can explain inertia in a better way? Any one of you can explain, raise your hand, and then we'll give you an opportunity to explain what is inertia. After that, we'll talk about virtual inertia. Can't they raise the hand so that we can unmute them?
Sir, it's Chandrasekhar, sir. Very good evening, sir.
Chandrasekhar, come. Tell me what is inertia? How the other friends can understand easily? Simplest way of teaching inertia.
I think the weight of a body is nothing but the inertia. If you just take the generator itself, the rotating part of that one is acted like as a inertia, which will depending upon the prime mover, it will assist to rotate or it may destabilize at one particular time and may lose the synchronization.
Somya Bangari, please answer. Somya Bangari, please proceed. You raised hand. So, Somya, can you hear me? All right. I think let us have an interactive session. Let me ask you a very simple example. Now, say today we like to connect a load of actually 1 megawatt. Okay. So we have connected a load of 1 megawatt. Probably to make it more interesting, let me consider a electric vehicle charging station. Electric vehicle charging station, which can charge 20 buses, which can charge 20 buses. And the load is actually close to 4 megawatt, assuming. Okay. So 4 megawatt of load, because the charger is not working all the time. Okay. Now suddenly there is a crowd, all the vehicles came to the charging station, and suddenly we switched on all the 10 charging points, at a time, assuming, which is not practically true, but anyway, if it happens suddenly, and they are all getting charged, how that 4 megawatt energy is being drawn by those 10 trucks simultaneously? I mean, I don't understand, because just before a millisecond, we were balancing both load and generation. The load and generations are balanced. Means whatever the load of, let's say, 500 megawatt, generation is also 500 megawatt. Now you made 500 become 504 megawatt load. So the generation is able to cater with 500 megawatt, the generation, with generation of 500 megawatt, the load of 504 megawatt is being met. Or anytime if you switch on the light, it says, no, 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 please wait. Does it say sometime? No, no. So we switch it on and it works. Very nice. God is so kind. So it works because normally what happens when you add load, the command will go to the thermal power plant, which is 500 kilometers away, and the thermal power plant will increase its steam. If it is a thermal power plant, then the valve is open, the motor will rotate. Okay. And finally, the synchronous generator will try to produce from mechanical to electrical power, and then it comes. And by the time all it comes, the buses or trucks might have left the location. So it's a physical system. No one can give 4 megawatts so easily. It is a system, no? But we are getting in milliseconds. If you answer this question, probably you'll understand what is inertia. Inertia means the capability of providing additional energy requirement in a system which is being stored in the rotating mass of the machine. Which is stored in the rotating mass of the machine. So that means so now let's say I have replaced 500 megawatt of load and 500 megawatt of generation. Instead of a synchronous generator thermal power plant, they become 500 megawatt of a PV park in Jaisalmer, Rajasthan. Okay. Now actually Mr. Manmohan switch on 4 megawatt extra. What will happen? It will say sorry. It will say sorry. The system will face challenges because no one can provide it. The PV system cannot increase its capacity from 500 to 504 because it will take some time to act. And by the time, so it will take, Manmohan, please wait for 5 seconds. I am creating generation for you and then it will be available to you. That is what we don't want, am I right? We do not want that to happen. So that means the inertia of the system is getting reduced day by day because of presence of photovoltaic or PV power plants where the rotational mass is missing. Right? So that is where the story begins with the virtual inertia, where can we extract some inertia from a system which is not having rotational mass. Am I right? There are some inertia available that people are not 4 megawatt, but at least 0.5 megawatt can be extracted, let's say. So if you say 4, it will say I can provide you only 0.5, sir, and give me 5 seconds to give you 3.5 megawatt after some time. And that is where the concept of virtual inertia came to action. All right. So hope everyone understood what is inertia, what are the challenges, who is responsible for inertia, and hence the importance of virtual inertia. That is the only reason people are talking about 100% renewable, but 100% renewable is next to impossible until unless there is a mixture of wind and solar. So if you have 60% wind, 40% solar, this is 100% renewable, but we can survive. But if there is a question, can we have 100% PV? The answer is straight no. Okay, excellent. So then we move to ancillary support, which is a very, very important concept. Ancillary support, it's kind of, if you are reactive, I will tell you many supports. In a system, we do some reactive powers, am I right, to meet out the loads, P and Q requirements. But everyone is generating P because they get paid for P. So if everyone generate P, what will happen to the system? Who will meet out my inductive load, Baba? How induction machine will run? Everyone is making money by giving real power only. So someone has to give reactive power, and there is no money for reactive power. So that's why reactive power pricing has been introduced slowly. Because previously it was government owned, and I do have a synchronous machine in which you have a PQ characteristic, and it is like a circle. You can have maximum Q, 0P, or I can have maximum P and 0Q. That is P square plus Q square equal to F square, which is a circle equation. But when I say money will be paid only for P generation, then I'll try to make my volt ampere equal to watt, so that I get maximum money out of it. But in the past, actually, when we have vertical integrated system owned by government in most of the cases, so that time what we used to do, government used to take the responsibility. I will give you the reactive power, don't worry. I will run 2-3 plants which will operate only on reactive power operation mode. So-called, for example, probably one slack bus, and probably there could be few generators belongs to government, NTPC, NSPC. That's what they are bankrupted, no? All giving help to people actually. Business people made money by selling real power, and government is giving only reactive power to help people, and they become bankrupt. It is not that they do not know how to make money, but it's a help they have extended to us. So my question here, that actually these are kind of support actually, we need to identify. Let's say there is a frequency challenge. Who will be taking the responsibility of providing frequency? Isn't it? There is a voltage variation issue. Okay? Who will provide the voltage regulation challenges? Man, someone has to cater. So today there is a cost associated for ancillary support. Nothing is free. If you give reactive power, if you support frequency, if you support voltage, you'll be paid for that. You might have heard about a machine called a synchronous condenser. Synchronous condenser is only responsible for generating reactive power. All the gas, oil, coal being burned just to generate reactive power. No money, but the plant being taken care. So today we have actually pricing for that. So smart grid, actually there are two important concepts. Who will support? Because reactive power is also mismatch, no? In a system. When you have completely PV systems, then you are not supporting any reactive power, support is missing. And inertia is also missing. So we need to extract who will take care of my ancillary, and how do I extract virtual inertia concept become very, very important in a given system. Very straight and clear, okay? So we have enjoyed AC/DC microgrid as of now, but we need to understand how those challenges which you're going to face, how they can be understood. Many times I say God is not very kind to engineers, not because of qualifying IAS or IS. If he's not qualifying IAS, he will say God is not very kind to me. It is not. God is not very kind to us because he's always giving a solution and also giving a challenge before us. Be free. But again, a time when you do not need it. It is free, but no reactive power. It is free and no inertia. Got it? Very good. So this is see how future power system evolving paradigm over the globe. Introduction of electricity generating source into distribution network historically contain only loads. And you could see the violet one is yesterday and the green one is tomorrow. That means how the system was in the past and how do we see the system for tomorrow. You see, previously we have very conventional power plant, coal, nuclear, like that, okay. Today we have wind, we have PV and many more things, okay. And the centralized, for these converters behavior fundamentally different from conventional synchronous machine, do not participate in the conventional control of the network. Powertronic equipment depends on the strength of the grid to which they are being connected and uncontrollable and intermittent in nature. Previously, it was very straight and controlled, but today they are uncontrollable and intermittent in nature. It is something like our new generation kids. Previously, most of them are controlled, and today, most of them are uncontrolled. Am I right? And previously, they are very stable, no aim. Whatever comes on the way, school teacher, uh, clerks, lecturers, bank employee, everything they are satisfied. But today, very intermittent, startup, cryptography, many, big things happening. All right, so integration of renewable energy sources, that is RES, you can say how renewable energy is being captured. I mean, these are the um, colors through which you can say how predominantly different countries, currently include hydropower, solar, wind, geothermal, and so on and so forth. So you could see India is actually not that bad. We are almost in between 20 to 30% of renewable integration. Am I right? So if you see North America is quite almost up to 30 to 50% of integration. Even I could see China and Australia, they are also around 40 to 50% range. So very good. So we are also not very far away. That's what I wanted to highlight. Now, outlook over available inertia. The interesting part of this talk is that, most of the informations, they will not find in textbooks as directly. So these are all making the talk quite interesting. So you could see there are two pillars actually. One is black one is the blue one actually. So inertia in European Union in almost actually 25% reduction happened. In Asia, close to 5% reduction. In US, it is 6% reduction. South America, it is 6.5. Why that inertia getting reduced? Because non-inertial devices are being implemented in the power system today. That is what the challenge is all about. And we now can say our outlook over available kinetic energy. There is an Indian scenario. So we could see because of renewable energy penetration and kinetic energy, we could see that over a period of time, there are a lot of drastic variation that happens within the year 2017, 18, 19, 20, 22. So as we increase the renewable penetration, we could see that the kinetic energy is slowly getting reduced. Now, inertia analysis under high renewable energy sources integration scenarios, application to the European interconnected power systems. This is what is being presented. So they say hydro, which is 10 seconds, and thermal, which is 4.75 seconds. And if you integrate RES in percentage, okay, so 5%, 15%, 30%, 45%, 65, 60%, you could see how the change in actually the time based on which you react to inertial challenges. One important part about the frequency support, which is an essential reliability support. So frequency represents an indication of the real-time balance between supply and demand. Declining frequency indicates more demand than supply, while rising frequency indicates more supply than demand. Frequency balance must be maintained within 50 Hz or 60 Hz, depending upon the systems. Now, ERS, effect of lack of ERS availability. So, essential reliability support, if you do not have in the system, then the frequency may fall. So, frequency support ensures that frequency of the system is stable for both normal and contingency conditions. Controlling frequency can be broken into 4 stages: inertial response, primary frequency response, secondary frequency response, and tertiary frequency response. Daily operation of system requires a continuous balance of load and resources. Operational flexibility is needed to manage real-time changes in load and generation. Now, what are the effects if you do not have actually reliability support? Large frequency deviation can result the equipment failure. Interconnection frequency deviation can result to loss of generation, load shedding, interconnection islanding, plus system stability and reliability at risk. Imbalance in generation and load can overload transmission facilities. Protection equipment can malfunction or be damaged. Prolonged imbalance can result to violation of reliability standards. Yes, please.
Yes. It's more.
Okay. I will tell you a very beautiful example to understand. Now you are riding a cycle, okay, with a speed of, let's say, 5 kilometers per hour. Now suddenly you saw a friend who jumped into your cycle. Have you experienced that in your childhood? Someone jumped into your backseat. What will happen? You vibrated and get slowed down. 5 become 3. So your frequency dropped because of the load increase. So that is what imbalance, no? Load increase or frequency drop. So that is how it is. All right, good. So frequency support, an essential reliability support ERS. So it is inertia, primary frequency control, secondary frequency control. You can see different definitions. For example, inertia definition: stored rotating energy in machine. It is accumulation of inherent response of conventional synchronous generation that arrest frequency decline. So what we wanted to highlight, as I told you, whenever there is 4 megawatt of load increase, so my frequency will drop from 50 hertz to 49.8 hertz, assume, or 49.95. So when the inertia energy is made available, okay, so then my frequency become 50 immediately. And by the time I produce, after some time, then that will go to my rotational mass saving. So first it will discharge, all right, and then it will capture it. So very interestingly, so the frequency regulation is possible with proper inertia balance. That's what I like to highlight. If you have proper inertia energy, then your frequency is not going to drop drastically in the future. What are the type of services provided inherently by synchronous machine? May be provided through deliberate control of RES, local frequency sensing applicable to virtual inertia only. And response time, it is in order of cycles. Now the same story, if you go for primary frequency, then it will go to in seconds, all right? And secondary frequency control, it is in the form of actually 15 minutes, almost in terms of minutes. Okay, so milliseconds, the inertia from the inertia energy, primary control will take 1 or 2 seconds, and then secondary frequency control will be in the form of in the form of minutes. So you can remember milliseconds, second, and minutes. And then virtual inertia and ancillary support, what and why. In order to counterbalance that decrease, the decrease in inertia, virtual inertia is utilized. When you experience inertia get reduced, then we proceed for virtual inertia. Virtual inertia is realized, I think, as a manner of Paltronics. Virtual inertia, your topic. Manmohan. Virtual inertia is realized by implementing the control function on the Paltronic interfaced renewable energy sources to mimic the CSG, inertial dynamics, and provide the inertia virtually. Now, the main source of virtual inertia is the short-term stored energy in the DC link. So DC link holds some energy, okay, of the RES power converters, which should be injected to the AC side according to the virtual inertia control objective. So what we do in a conventional system, we extract the inertial energy from a synchronous machine, okay? Suddenly but here there is no moving part, okay? So that case, the DC link energy through interlinking converter, we can push that virtual energy to the AC link so that most of the loads can be met.
Storage.
Hmm?
It has storage.
Not storage. Storage is a different thing. But here actually, because all your inverters, all power alternate devices do have some storage, some energy capacity, they're not using it immediately. But they can dispose of to the AC grid in the form of actually millisecond transformation, so that your synchronous machine characteristic can be experienced on a power turning circuit. That's what they are saying. So in a AC/DC microgrid also, one can evacuate the energy being stored through power turning devices that can be evacuated under emergency.
Devices will also extract from.
First, actually, they will immediately meet out this condition, and then they will get it wherever it is available. Okay, probably they can take from the PV source and store it after some time, but immediately they will support the system. All right. So you could see those diagrams. So there is a comparison I'm just trying to make. You have a synchronous generator. Lot of good research happened in this area. This is a very good PhD topic. So you could see there is a synchronous machine. The same synchronous machine phenomena can be experienced through a converter. All right. So you could see in the synchronous machine, there is energy conversion, there is a turbine, and there is a frequency control happens. Okay. And the energy conversion happens in case of a converter, and you have controllers. So controllers, AC voltage control, and your synchronous machine evacuate your inertial energy or frequency regulation. The same thing can happen in case of DC, but the magnitude here is very, very low. It's not a very high power inertia energy. You could see there is a very interesting table which talks about generation types and capability of grid stability, conventional synchronous generation, which gives you inertia and active power control, similarly DFIG, then PMSG, but you could see PV array, which is not doing the inertia, unfortunate fellow, isolated, and then battery storage and demand response, they all work it. So application of European interconnected power systems, and you could see that a lot of interesting things. The right-hand side, with different renewable energy, okay, the frequency, how it faces, So 5% and then 30% and 60% of renewable energy penetration, we could see that how the frequency dropped at different levels, 49.22, 21, 25, and so on and so forth. We'll take one interesting example for our IIT Roorkee campus. We have done a bit of research. I'll tell you slowly after some time. Limitation of RES and demand response for frequency support services. Possible no power generation from RES during a frequency event and intermittent nature of renewable energy sources. Uneconomical to operate deloading mode. Am I right? So frequency to support frequency, I cannot deload my renewable and switch on something else. limitation of demand response, complexity involved in sophisticated communication and control mechanisms required for demand-side contribution, unpredictable customer behavior. Apart from above-mentioned point, total amount of provided flexibility does not entirely compensate, okay, of the for the substituted CSG. Also, four major ancillary support cannot be provided simultaneously by renewable energy sources and demands responses. So what they are saying, demand response means you can compromise some loads and you can shift some of the loads and behave differently. And so they say nothing is possible. With renewable energy, there are a lot of challenges. So the question is, what are the solutions? I think there is another PhD problem opening. All right. And that is where the virtual inertia and ancillary support from virtual synchronous generator. Okay, VSG is a very interesting problem. Many good research has happened. So virtual synchronous generator is nothing but a Baltronics device concept which mimic my synchronous machine. So BSG are a control application for enabling converters and inverter-based technologies to mimic the behavior of traditional synchronous machine, including reciprocating diesel generators, gas turbines, and synchronous condensers. BSG provide many of the same grid stabilization services as traditional generators, including system strength, system inertia, frequency regulation, and voltage support, and are unique in their ability to be tuned via software adjustment. So all of you can have a look. So we have a machine, okay, on the top, which is being replaced by your complete inverter setup from a DC bus to a power grid. Okay, this is a very, very exciting topic, but the only question is, a lot of good research happened already. So someone to start with actually must spend 2 to 3 years time to understand, is there any gap further? It has been very nicely explored. Some of my scholars spent a lot of time and could not find any good thing out of it. So virtual inertia and ancillary support from VSG, as you could see, inertia, system strength, voltage control, and frequency control. So these are the elements actually which supports, for example, inertia, synchronous generator, battery energy storage system, synchronous condenser, SPDC with voltage source converters, new wind farms with controls. They support inertia. And frequency control comes from the battery, HPDC, wind plants, and load setting. And system strength that comes from synchronous generator, BSC batteries, synchronous condensers. And finally, the voltage control comes from synchronous generators, batteries, synchronous condensers, STATCOMs, capacitors, and then load shedding. Okay, this is how the system works. Now we'll move to a small case study of IIT Roorkee campus. Probably we'll talk more detail on this system itself in future. So as you all know, actually this is close to 8 megawatt system, all right? And we had actually currently we have 2.8 megawatt of renewable energy available. But this case study has been, performed with the older data, because the data 1.73 megawatt of actually, renewable energy, PV. So the system has been, this analysis is with reference to 1.73 megawatt of. But then slowly they have been actually reworked out with actually the major chunk of actually 2.8 megawatt of renewable, because if you have maximum renewable, then only you can foresee the inertial challenges. Otherwise, it will not be more effective. So you see, we have finally considered, we started with 1.73, finally we reached to 2.8 megawatt of PV with 35 locations. And you could see there is a diesel generator. Okay, we have 4.5 megawatt of diesel generator, and the VSG of 1.5 MVA, which has been realized, okay, for the research purpose. So I think 2.8 megawatt and then 1.5 MVA VSG is in place. and then the research begins. So virtual inertia from VSG with BSS and increased integration of RES in islanded IITR Roorkee distribution system. So we assume the system is islanded. So we are completely free from inertia. Little bit of inertia can come from generator. Then we have a VSG, we have complete PV system, and the system has been carried out. So RSCADE study of IITR distribution system, runtime window. So first of all, it need to be simulated in RSCADE. So you know what is RSCADE? It is basically the software similar to PSCADE, works on a RTDS system. So these are the simulation results. As you could see, interpretations, frequency, which is 50.12, small inertia, large inertia 50.1, and bang is 50.08. We have gone for a increment in load, 30 kilowatt to 70 kilowatt. Then we realized the frequency dropped, which is small inertia 49.88, large inertia 49.9, and bang is 49.88. So the settling time, you could see it is keep on changing, and these are all equations, quantification of inertia. How do you quantify with all BSGs and batteries and renewable energies? So I strongly recommend to read one of the article by Apruti Jain, if I'm correct. We have also validated PHIL for this virtual inertia concept. So it's a real-time story, yeah. So then probably you could see last one, the sixth one, where it talks about Apruti Jain, myself, and Professor Pathak. A wonderful article which talks about quantification of inertia contribution from non-conventional source in AC microgrid. Okay, so probably after that, she is currently with the GE, and couple of two transactions which has come afterwards. You can look into the inertial concepts. So you can refer to A. Jain, Apruti Jain, probably you'll get good references in this topic. So with this, we come to an end today. Very interesting. Hope Manmohan case, how do you enjoy today's lectures? And slightly different than the conventional topic. Okay. So it is not about a concept, but we have also concluded that this is realizable, this is implementable, and being already done it in the laboratory level. So, but it took almost 3 to 5 years time to achieve all this. Thank you very much for your kind attention. Any questions? We can take a couple of questions from the student, if any.
Good evening, sir.
Go ahead. Introduce yourself.
Sir, I'm Rakesh Shukla from Government College of Engineering, Keonjhar, Odisha.
Oh, go ahead, Dr. Shukla.
Sir, in DC microgrid, where only renewable energy sources are there, so how we can introduce the concept of this inertia here by taking which device introducing?
So actually, first of all, if your system is completely free from rotational devices or power generation, then indirectly you don't have any inertia with you. Okay, so that case probably in a larger system it is quite risky, but smaller system we can manage. But that's what you talked about, virtual inertia or synchronous generator, VSG. So VSG is a concept which talks about a replacement of a machine, synchronous machine, or indirectly an inverter can act as a VSG, okay, with proper control strategies. So you can extract energy from an inverter similar to a synchronous machine with a very low magnitude, and you can minimize your frequency drops or regulation challenges. All right. So if it is an isolated system, it's different. But certainly all the inverters can be, is a micro synchronous machines, you can say. Okay, we can extract some inertial energy from it. Is it okay?
Okay.
Suklaji, is it fine?
sir.
Good, good. Next. Any other question? That's all. Okay. Thank you very much. Take care.